Go ahead and get started. I know I originally said that we're going to go ahead and do some more atomic mass, molar mass, or excuse me, formula mass, molar mass calculations, and talk about percent composition. However, we will be doing more of that later on when we really start getting into the stoichiometry. So instead of spending time right now doing that, I decided to go ahead and get into Lewis structures, and then when we get to stoichiometry, we'll do a couple more examples. So, any questions? I know on the last homework there was the calcium bisulfate issue. I did go in, and anybody that actually said calcium bisulfate, calcium bisulfate, I was able to give them full credit for that question. So, so that is where we stand. Okay, so we're going to get into Lewis structures. Lewis structures are simply a way to represent the electrons that are responsible for an element's reactivity. That's what a Lewis structure is. Now, if you'll recall, when we were talking about electron configurations, one of the definitions that you were given were the valence electrons. The valence electrons are the electrons responsible for an element's reactivity. So when we develop a Lewis dot structure, we're focused on the valence electrons. At that time, when we were talking about valence electrons with respect to Lewis structures, we looked at it with respect, at the time when we were determining the valence electrons, we were looking at the electron configurations, and the valence electrons were the electrons in the highest shell. And we simply would look at the electron configuration to determine how many electrons were in the highest shell. But there is a simpler way, and we will be using that simpler way because for the most part, we are going to stick to group 1, 2, group 13 through 18 atoms from now on for Lewis structure purposes. And the simplest way for the main group elements is that the number of valence electrons in the main group elements is equivalent to the last digit of the group number. This is not true for your transition metals, but it is true for, again, the main group elements, which again is group 1, 2, and 13 through 18. So for example, hydrogen is in group 1. Hydrogen has 1 valence electron. Fluorine is in group 17. The last digit is a 7, so it has 7 valence electrons. Xenon is in group 18. The last digit is an 8, so it has 8 valence electrons. So again, the number of the Lewis structure is a diagram, a picture that demonstrates how the valence electrons interact. So we need to be prepared to determine who the valence electrons are. And if we're talking about the main group elements, that's the number of valence electrons is going to be equivalent to the last digit of group number. Now, before we get into the Lewis dot structures or the electron dot structure of an atom, the next thing that we need to realize is when developing the Lewis dot structure of an atom, there are really 3 parts. The first part is the element symbol. The element symbol does tell us the identity of the element. But in the case of Lewis dot structure, it also represents all of the core electrons. So the element symbol, when we start developing the Lewis dot structure, the element symbol is going to represent the identity of the element as well as all the core electrons. The second part is an imaginary box around the symbol. We typically won't draw the imaginary box, but it just gives us a outline. The last part are the dots. The dots themselves represent the valence electrons. Now, with these dots, you place one on each side of the box before pairing. Note, it doesn't matter where you start. So let's just look at some. We have hydrogen. We're going to have an imaginary box around our hydrogen. Hydrogen is in group 1. So it has one, the last digit is a 1. So it has one valence electron. So we place one valence electron on it. Helium. We have an imaginary box. Helium, now helium is an oddball. Helium only has 2 valence electrons because it's a 1s2. So you're going to place one on each side of your imaginary box, and they can go side by side. We could have done it where instead of them being side by side, they were across from each other. It really doesn't matter. Again, it doesn't matter where you start. You just place one on each side before pairing. Lithium is in group 1, last digit of 1, so it has one valence electron. Beryllium is in group 2, its last digit is a 2, so it has 2 valence electrons. Boron is in group 13, the last digit is a 3, so it has 3 valence electrons. Carbon is in group 14, the last digit of 4, so it has 4 valence electrons. Nitrogen is in group 15. It has, last digit is a 5, so it has 5 valence electrons. Again, we place one on each side of the symbol before pairing. So nitrogen is the first of the elements that has a paired electron. Oxygen is in group 16, the last digit is 6, so it has 6 valence electrons. Fluorine is in group 17, the last digit is a 7, so it has 7 valence electrons. And neon is in group 18, the last digit is an 8, so it has 8 valence electrons. Again, the only element that is not, that does not follow this was our helium. And that's because helium only has 2 valence electrons to begin with. Questions about drawing the electron dot symbol for an element? Now, I love doing this because the electron dot symbol predicts the most common number of bonds for the nonmetals and metalloids. You may ask how it predicts it. Well, the number of open spaces in the electron dot structure frequently equals the number of bonds that can form. So for example, carbon has 4 open spots. Carbon tends to form 4 bonds. Nitrogen has 3 open spots. Nitrogen tends to form 3 bonds. And I do say tends to because there are exceptions to rules. But on average, oxygen has 2 open spots, so oxygen tends to like 2 bonds. Your halogens have 1 open spot, so they tend to like 1 bond. And your noble gases tend to have 0 open spots, and that's why they tend to not form any bonds. Xenon is the first noble gas that will form a bond, and the only reason, and part of the reason it will, is because it's so big. But on average, it helps you to predict. Yes.
So I did come a little late, and I don't know. So it says on for the electron Lewis dot configuration, it doesn't matter what side you start.
Correct.
Does that mean when you start pairing, you just pair where you started again?
I usually do, but it doesn't matter. You can pair up if you want to, as long as you put one on each side before pairing. Other questions? That's all there is to the Lewis dot structure of an atom of an element. So that is pretty straightforward. Now let's talk about Lewis structures. For ionic compounds. Some people will say that you can't make a Lewis structure, but other people will say you can. So we're going to go with the can side. Okay. So to begin with, we're going to develop the Lewis dot structure of the atoms. Of the elements in the compound. Then the metal is going to give away its valence electrons. The nonmetal is going to accept its those valence electrons. So take sodium chloride. Sodium is in group 1, so it has 1 valence electron. Chloride is in group 17. The last digit is a 7, so it has 7 valence electrons. So we've drawn the Lewis dot structure of the atoms of the element. Now what we're going to do is we're going to give away sodium's electron, and it's going to be given to the chloride. So since sodium has 1 electron, 1 less electron, it is now positive. And the chloride, because it has an additional electron, the chloride itself is negative. You'll either see sodium chloride written in this format if you're talking about Lewis dot structures, or you may see it written as this, or written in this format. Either one is perfectly acceptable. So let's talk briefly about this structure. Basically, when we develop ions, the element symbol is in brackets. Along with all its valence electrons. And then the charge is a superscript to the right of the bracket. The only time that this can be omitted, these brackets can be omitted, is if you're talking about a cation, because a lot of times those cations, they have no more valence electrons left. Let's look at calcium chloride. Calcium is in group 2, the last digit of 2. Chloride, well, first of all, calcium chloride is CaCl2. It has, chlorine is in group 17, so it has 7 valence electrons. And there are 2 of these chlorines with 1 calcium. Again, the metal is going to donate its electron, but chlorine can only accept 1. It has only 1 opening. So that's why we have 2 chlorines, is because we need to be able to accept 2. So in this particular case, you may see it written as Cl minus, Ca2 plus, Cl minus, You may see it written as Ca2 plus and 2 Cl minuses. Or you may see it written as the chlorines followed by the calcium followed by another chlorine. These are just different ways you might see it written. Yes.
Will you accept any of those on the test?
On the test, I'll accept any of those. I believe for actives purposes, first of all, it's multiple choice because there's only like one question on the entire thing that I can get. Active will either do it. Well, if I can make my pen behave. They'll either use the first one or the second one, and I cannot remember which one the third one. And I cannot remember which one they use. I want to say it's the third one, but it's been a while since I looked at it. Let's look at one more of these. Let's look at calcium oxide. In the case of calcium oxide, again, calcium has 2. Oxygen is in group 16, the last digit is 6, so it has 6 valence electrons. Calcium being a metal, we know donates its electrons. Oxygen needs 2 electrons to form an octet, 8. Calcium has 2 electrons to give up. So it's in a 1-to-1 ratio, and therefore the formula for calcium oxide is going to be Ca2 plus O2 minus. Questions? Yes,
Is it 2 plus because you took away 2 valence?
correct. It's 2 plus because I took away 2 valence electrons, and it's 2 minus because I added 2 valence electrons. And electrons carry with them negative charges. Other questions? Okay. That is all there is to ionic compounds. I will be keeping it to group 1, group 2 for the metal, or aluminum, gallium, and indium. Aluminum for the metal. So in other words, there won't be many choices for the metal. And I know for the test, I'll keep it to a elemental anion. Now, folks, you don't have to draw out everything I did. When I look at a test answer, what am I looking for? If I'm looking for a test answer, I am just looking for the result. You don't actually have to show me everything that went into it. I'm not saying you cannot. You can still do all that. But I'm looking for the answer. Okay, so that's actually a very small category. Ionic compounds, folks, is a very, very tiny, tiny, tiny category of compounds relative to covalent molecules. Part of this was discussed when we were starting the covalent molecule discussion, with the fact that when we talk about covalent molecules, they arise through the sharing of electrons. And because electrons are shared, you have a whole lot more choices out there than you do with ionic compounds. So what we're going to do is we're going to start by developing this concept. Now, as I do the Lewis dot structure, of covalent compounds, for today's class, there is going to be one key thing that I ask myself. Now, as we will see, we're going to expand upon this come Tuesday of next week. But for the purpose of today, and given the amount of time I have, there's going to be one question that I'm always asking myself. And that question is, does everybody have an octet? With the exception of hydrogen, which needs 2 electrons, and boron, which needs 6 electrons. But the rest of them, I'm going to be asking, does everybody have an octet? That's the question. Because everybody else better have an octet. Okay, we're going to take a 5-minute break and stand up and move, because I've got a lot of sleepy faces. And maybe if you move for 5 minutes, we can come back and focus for the rest of the time. And Luna Bear can come say hello. Oh, she got excited about that. Let's go say hello to everybody. You ready? Okay. Say hello. That's what it's like. You want to say hi? Say hello to everybody. If they want to say hi to you, they just stick out their hand. Just say hello. Anybody that wants to say hello to you. Say hello. It has to do more with first of all, it always has to be, you cannot make so you can make that more, but it winds up with the most charge. Because of yeah. I'm saying hello. Your kids want to they want to say hi.
They want to say hi. Where you going? Come here, over here. Up here. There's his hand. Happy right now, Lisa? Come on, let's say hello some more. Anybody want to say hello? Let's stick up your feet. Good girl. Come on. How long way to go? Where you going? Come on, silly girl. Oh, you just come here. Right here. You walk it. Want me to go that way and then this side? Come over here. Say hi. My tail's just wagging. I'm so happy today. Hey, Luna. Here, come here. Where'd you go? Okay, so I can. Say hi to Dad. Let's say hi to Dad.
She looks so much like our Beagle. So ours is like black. That's
Very good. Come up the aisle, we've got a little bit more, then we gotta get busy again. And say hello, you want to say hi. Somebody said your name. And just stick out your hand on it. That way mama knows you want. You got a hand? Over here. Right here. Okay, cool. Okay. Almost back. Back to your bed. Back to your bed. Good girl.
Okay. Where are you going? You come back to your bed. Do I have to put your leash back on you? Come on. Lay down. Lay down. Good girl. Okay. So let's get into these Lewis structures. And as I do so, I will be developing some terminology as well. So we're going to start with the simplest of all molecules, and that's going to be that of hydrogen. Hydrogen is a diatomic element. Remember, you've got, for your diatomic elements, there are 7 of them. Brinkelhoff, the H being one of them. So it's diatomic, so it always comes in a pair of 2. So if we develop the Lewis dot structure for an atom of hydrogen, each hydrogen has only 1 electron. Now, because hydrogen is a non-metal, it forms covalent bonds. Covalent bonds arise through the sharing of electrons, where 1 electron from each hydrogen atom is brought into the middle to share between the 2. So what arises is a structure that looks like this. Now, the hydrogen on the left views those 2 electrons that it is sharing as belonging to it. And so it says, aha, I have 2 electrons. The hydrogen on the right views those electrons as belonging to it. So it goes, aha, I have 2 electrons. So each hydrogen has a share of 2 electrons. And for hydrogen, it only needs 2 electrons. So it says, I'm done. So if I'm writing the Lewis dot structure, I could write it in this format, but dots take a long time to write. So one of the things that we represent is a pair of dots will be represented by a single line, and it's called a single bond. So instead of hydrogen being written with 2 dots, we'll write it with a single bond in between the 2, and it means the exact same thing. So 1 line means 2 dots. Okay, another element in that Brinkelhoff is oxygen. Oxygen is a non-metal. We have 2 non-metals. That means it's going to be a covalent compound. If we draw the Lewis structure for each oxygen, we're going to see that oxygen has 6 valence electrons because it is in group 16. The last digit is a 6. Now, we always start by doing a share of 1 pair. So we're going to bring in 1 pair of electrons from each of the oxygens. And when we bring in that pair of electrons, the structure that arises is this structure. Now, the left-hand oxygen sees that it has a total of 7 valence electrons at this point. It's not happy with 7. The right-hand oxygen also sees itself as having 7 valence electrons. It's not happy at this point either. So this is not the structure for oxygen. Now, to make it easier, I'm just going to rewrite this just real quick so that we can see the next stage. So our oxygen is going to bring in another pair of electrons to share between the two atomic nuclei. When that occurs, it now has 4 electrons that are shared between the two atoms. The left-hand oxygen sees itself as having 8 valence electrons. That is the octet. So it is happy. The right-hand oxygen also sees itself as having ownership of 8 valence electrons. So it too is happy. Now, the sharing of 4 electrons between the same 2 atomic nuclei is represented by 2 lines. Again, remember, a line represents 2 electrons. So 2 lines would represent 4 electrons, and it is called a double bond. So typically, we will write this oxygen with a double bond in between the 2 atomic nuclei. Now, folks, just like before, when I said it really didn't matter where you put the electrons, I drew it here, but you may see it drawn where they're at an angle, which is technically more accurate. You might see it drawn like that. All 3 of those are correct. Questions? Yes.
So if we were given a problem like that on the test, would we ever see it like with a single bond instead of the 2? Like,
For just pure oxygen? No. Now, when we get into other molecules, yes.
okay.
But for just pure O2, no. It'll always be a double bond. Let's look at another one. Let's look at nitrogen. Again, nitrogen is one of your diatomic elements. Nitrogen is in group 15. The last digit is a 5, so it has 5 valence electrons. We start by sharing 1 pair of electrons between the 2 atomic nuclei. Right now, if you're only sharing 1 pair of electrons, the left-hand nitrogen views itself as having 6 valence electrons. And again, it is not happy. And the right-hand nitrogen views itself in the same boat with 6 valence electrons, and therefore it's very unhappy. So nitrogen does not share 1 pair of electrons. So let's bring in another pair of electrons to share. When nitrogen brings in a 2nd pair of electrons to share, the structure that arises is this structure. The left-hand nitrogen sees itself as having 7 valence electrons. Well, that's better, but it's still not what it wants, which is an octet. And the right-hand oxygen sees itself as having 7 valence electrons. Again, better, but not where it wants to be. So we bring in a third pair of electrons to share between the two atomic nuclei, and the structure that arises is this structure. Now the left-hand nitrogen sees itself as having 8 valence electrons, and it is happy because it has its own 2 on the left-hand side, but it has 6 in between. The right-hand nitrogen sees the same thing. It has its 2 that belongs to strictly it, but then it also has the other 6 in between. So it has 8 valence electrons, so it is happy. Now, 6 valence electrons shared between 2 atomic nuclei is represented as 3 lines, because again, each line represents 2 electrons, and it is called a triple bond. So more than not, you're going to see nitrogen written in this format where it has a triple bond. So I've introduced 3 pieces of terminology: single bond, double bond, and triple bond. Technically 4, because I also introduced the concept of an octet, which means 8. Now I'm going to introduce 2 more pieces of terminology, and that is, these are bonding groups or bonding electrons. And these are called lone pairs, which is actually a little bit deceiving because you can also have a lone electron, as we will see when we get to some molecules. And if you have a lone electron, then that lone electron is called a free radical, which is highly bad, highly dangerous. So terminology wise, bonding electrons or bonding groups, lone pairs, the triple bond and what it means, the double bond and what it means, and the single bond and what it means. Then we also have the term octet, which means 8 electrons. I use hydrogen, oxygen, and nitrogen to introduce the terminology, but we are going to use this process in developing molecules too, not just diatomic elements. So let's look at water. Now, before I really get into water, actually, let's talk about some steps in developing Lewis structures. One, you're going to add up the valence electrons. For each atom in the molecule. Two, you will determine the central atom. Now, I will say that typically it's the first element listed. Unless that element is hydrogen. Then you go to the next element. Once you've determined who the central atom is, you will write the central atom. And place all other elements around that central atom. Now, I will say this holds true, but there can be more than one central atom, which we'll discuss a little bit here and a little bit there, but for the most part for this course, there's going to be one central atom. 4, you draw a single bond. Between the central atom and each outer atom. You then subtract 2 for each bond drawn from the total in step 1. Then you place all additional electrons around the outer atoms. Okay. As long as you can see, we'll be okay. Giving the outer atoms an octet. If electrons still remain, they are placed on the central atom in pairs. Okay, so now we'll look at water. There's more to this than that, so we'll be adding to that list. For today, we will not add to that list. H2O. H2O, we know, has 2 hydrogens and 1 oxygen based on the formula. Hydrogen is in group 1, therefore it has 1 valence electron to distribute. And oxygen is in group 16, the last digit is a 6, so it has 6 valence electrons. The hydrogen gives us 2 valence electrons, the oxygen gives us 6 valence electrons total, to give a total of 8 valence electrons. Step 2 said to determine who your central atom is going to be. Typically, it's the first element listed unless that element's hydrogen, in which case you go to the next element in line. Since the first element listed is hydrogen, we go to the next one in line, which is oxygen. So our oxygen is going to go in the center, and then step 3, we're going to place all other elements around that central atom. Step 4, you're going to draw a single bond between the outer atom and the central atom, and we're going to subtract 2 for each bond we drew. We drew 2 bonds, 2 times 2 is 4. So we're going to be subtracting out 4 valence electrons due to our bonds to give us 4 valence electrons. Still remaining to distribute. The next step says to give your outer atoms an octet. How many electrons does hydrogen need to achieve an octet? 2. Does it have 2? Yes, because remember, a line represents 2. So each hydrogen currently has 2 valence electrons within the bond that it shares with oxygen. The next step says that if any electrons remain, they go on the central atom in pairs. We had 4 electrons remaining, so we placed those 4 electrons on the central atom in pairs. And we hit 0. When we hit 0, we asked, does everybody have an octet? When you hit 0, you ask, does everybody have an octet? We know that the hydrogens do because they only needed 2 to achieve the octet. How many does oxygen need for an octet? 8. Does it have 8? Yes, because it has 2 in each of the bonds, making up a total of 4. And then it has 4 in the lone pairs on it. So it has 8 valence electrons. So this is the Lewis structure for water. Let's look at methane. Methane is CH4. It has 1 carbon and 4 hydrogens. Carbon is in group 14. The last digit is a 4, so it offers up 4 valence electrons. Hydrogen is in group 1. The last digit of 1, so it gives us 1 valence electrons. The carbon contributes a total of 4 valence electrons to the structure, and the hydrogen's 4 valence electrons, meaning we have 8 valence electrons to distribute. We then determine who our central atom is going to be. Folks, carbon is always the center of attention. It is always the central atom. it does not matter where it comes in the formula, it's going to be the central atom. So we're going to take our carbon and then we're going to place the hydrogens around the carbon. We are then told to draw a single bond between each of the between the central atom and all of the outer atoms. We drew 4 bonds. 4 times 2 is 8. So we've used up 8 valence electrons in bonds. At this point, we hit 0. We asked, does everybody have an octet? And the answer is yes, because the hydrogens each have 2 valence electrons in their bond. And the carbon has 8 valence electrons because it has 4 single bonds, each containing 2 electrons. So this is the structure for methane. Questions? We're going to get out 10 minutes early because we're about to get into some multiple bonds and everything. And I haven't gone over that yet. And I don't want to write the rules and confuse you. So I'm going to bring in rules. But also, folks, maybe after fall break, your brains will be a little bit more rested and ready to go. I will see you then.